As a mathematician, I'm not completely convinced that black holes exist. I mean, they're very strange objects, singularities, God knows what. So I decided to check if they do. And of course, if it exists, it must exist on Amazon. So I went to Amazon and saw if I could get a black hole. And believe it or not, they do exist. In fact, there's one right here. Be careful. So we got your black hole so that you can have it. Here it is. You can. It's a carpet that you can put in.
Oh, I love
And
it.
it's a black hole. So you can have that.
All right.
Now, I'm told also that these days it's very fashionable to have two black holes, right? Because these people like about doing something. I think they're supposed to move in some strange way. I don't know. Anyway, so we got you a different one. I'm told it's better if they're different sizes because that's kind of interesting, right? So we got you a smaller one.
Oh, awesome.
So
All right.
I don't know if they're going to start moving here. I don't know.
Prepare to orbit. Or merge.
Anyways,
Thank you.
it's a great pleasure to have you. Welcome. Thank you so much.
Oh, thank you very much for that lovely introduction. And it's really a great pleasure to be here today to speak to you in person. This is my first lecture in person at UCLA. And it's so nice not to be speaking to that green dot at the top of my screen. I have to get going by thanking one of the grad students in the Galactic Center Group who's agreed to run the slides from the back. So I'm also doing this talk blind. So another first. We'll see how well I know my talk. So as you learned, I actually did go to college wanting to be a math major because I really viewed math as the language of science, the language of puzzle solving. And I ultimately see my job as a scientist as one of figuring out the puzzles. In this case, it just happens to be puzzles about the universe. And I've had the great pleasure of consulting various people in the math department over the years about how to deal with data, statistics properly. So I'm grateful for that collaboration and the ability, especially in the old days, to just walk down the hall to some of the brightest in the field. So I came to UCLA in 1994 because what I wanted more than anything else in the world was to get access to the Keck Observatory. Keck Observatory is the largest telescope in the world. It's co-owned by the University of California and Caltech. So if you have the best tools, you can do the best science. So for me, coming to UCLA is absolutely my dream job. And what makes UCLA so special, in addition to being a partner in this telescope, was at the time, just before this facility opened, UCLA did some just wonderful strategic planning about how to play a leadership role in this facility. In particular, recognizing that Southern California was just brimming with people investing in infrared technology thanks to the aerospace industry. So there was a move to invest in people interested in the technology and methodologies associated with infrared astronomy and astrophysics. So I'm part of that initiative. It was an effort to collectively hire several faculty who together would really focus on this area. And it was a brilliant move. It's really brought UCLA into very much a leadership role in this great facility. We've built, I think, every infrared instrument on this facility, and that's roughly half of all the instruments. So I'm really grateful to be here and to be working at such a visionary institution. Now, having come here in 1994, actually UCLA took a big risk on me. I'm looking at the dean. I was 1 year out of a PhD program, so I was incredibly young and probably naive in terms of not understanding how hard things would be, but there's a beauty in being naive, which is you just think you can do anything. So my vision was to study black holes with this new facility and to use this facility in a new and different way. So Rory, if you could go one slide forward, that would be great. So this is a picture of the team right at the outset, and I really want to give lots of credit to my long-term collaborators that are shown on the left of the slide, Eric Beckland and Mark Morris. Eric was hired actually is part of this initiative, and Mark was part of the group that understood that this was a great direction to go in. So they've been part of this program for the last 25 years, and I'm very grateful. But it was a very small, lean group. On the right is my very first graduate student, and we thought we had a great idea. We were going to use the big telescope in a new and different way and discover a black hole. Well, unfortunately, the original review committee said, we're not convinced. So in fact, this was turned down. Not only was it turned down, and I really want to emphasize this to the students, just because being in basic research, it's not always smooth sailing. You know, you have to kind of believe in your ideas enough to overcome the obstacles that are inevitable along that trajectory. So we definitely started with a big bump. But of course, at this point in my career, I was also already quite used to bumps and knocks in the night. And my favorite expression today is every challenge is an opportunity. So what was the opportunity? The opportunity was to give lots of talks up and down the UC system to convince people that we knew what we were doing, that we could use the telescope in this new and different way. And our vision was a project that would only last 3 years. So that's rather amazing in itself too, because today, 27 years later, we're still going strong. And we're still going strong with a much larger team. So if they didn't want to give us time before, they didn't know what was coming. So Rory, could you go to this? So we're now a group of roughly 30 collaborators or core scientists that are the core of the mission. And we have about 100 collaborators from all around the world. So not only are we looking at the frontier of science in terms of our understanding of black holes, but we've also become a group that advances the technological development of both the Keck Observatory and then the coming project, which I'll talk about at the end, the 30-meter telescope project. Okay, let's go one more. Okay, so there are two perspectives on why what we were trying to do was interesting. And what we were trying to do was measure the orbits or motions of stars at the center of the galaxy, which really in the first place was to even discover that they existed. From a physics perspective, sort of a fundamental physics perspective, the reason this is an interesting thing to do is we can prove that really massive black holes, what we call supermassive, and I'll get back to what I mean by supermassive, exist in the universe. These are real, I'm going to say more in a second. And today, this has turned into the question of how does gravity work near these exotic objects. Okay, so this fundamentally boils down to understanding how two fields in physics come together, because today, they don't. We don't know how to make quantum mechanics, which is the study of things that are very small, work together with general relativity, which is the study of things that have lots of gravity, and black holes have both. So really, black holes represent the idea of this is the path forward for furthering our understanding of fundamental physics. Can we go forward one more? So the second perspective of why this is an interesting perspective comes from an astrophysical or an astronomy perspective. And it's getting at what role do supermassive black holes play in the formation and evolution of galaxies. While a decade ago, when we were first reporting some of our findings, it used to be thought, or people used to think of the relationship between galaxies, which are the fundamental building blocks of the universe, and these really big black holes. People pose this, or it as a question, what's the relationship? Which came first, the black hole or the galaxy? And that's very much like the chicken or the egg question, which came first. And of course, we had theories for both. But what we've figured out today is it's just the wrong framework. That the mass of these black holes seem very correlated with the mass of the central part of the galaxy. And the scales are so vastly different that it's hard to imagine one causally relating to the other. So today, we think that whatever formed the galaxy formed the black hole synergistically, and that there's some feedback mechanism between the two that keeps the growth of both the black hole and the galaxy in sync. So we really have an amazing opportunity today to understand this intimate relationship between the host galaxy and the central black hole. Okay, can you go forward one more? Okay, so let's go back a few steps and ask the question that I like to ask at the beginning of public lectures, which is, how do you observe something you can't see? This seems like a fundamental question if you want to find and study black holes, because black holes are objects whose pull of gravity is so intense that nothing can escape them, not even light, so you can't see them directly. Next. So it always seems appropriate to show an absolutely blank slide if you want to explain what a black hole is, because we know very little, actually. And they're actually amazingly simple. So while black holes require relatively exotic physics and mathematics to describe, the way I'd like you to think about a black hole today is to think of it as an object whose mass is confined to 0 volume. So if you think about density, which is just mass divided by volume, the volume goes to 0, which means density goes to infinity. And in physics, anytime you have a number going to infinity, that's known as a singularity, or equivalently, a big giant red arrow that says you do not have your description of the physical world correct here. In other words, it's worth pursuing. Okay, next. Okay, so as I said, this fundamentally represents our inability to make these two fields work together. Next. So while black holes have no finite physical size, there is an abstract size that one can associate with these black holes. It's known as the Schwarzschild radius. It's also known, or has been popularized by Star Trek, to be the event horizon, the last place light can escape, which means that no information can travel from inside this radius to the outside world. It's also a really important concept for 2 other reasons. One is that every object that has mass actually has a Schwarzschild radius associated with it. You do, your neighbor does, your cell phone does, and the key is, it just depends on the mass of the object. So if you can squeeze that object down to the scale of the Schwarzschild radius, that's the scale at which gravity is going to overcome all other known forces and force the object to become the infinitesimally small object known as the black hole. It's therefore the radius, or it really contains the keys to understanding how do you prove that there's a black hole out there. You need to show that there's a lot of mass inside a very small volume. And ideally, you'd get down to the Schwarzschild radius associated with that mass. Okay, so now let's consider how big this radius is for different objects. So Rory, could you go the next one? Okay, so if we could take the Earth and squeeze it down to the size of a sugar cube, and I realize I should find a better analogy because most people aren't using sugar cubes these days. Can you tap forward? So we're going to squeeze it down to the size of the sugar cube, put a giant compressor. That's the Schwarzschild radius of the Earth. It will become a black hole. Now, the Schwarzschild radius scales linearly with mass. So if you double the mass, you're going to double the size of the Schwarzschild radius. So if you go to the next slide, we're now going to consider the sun. If you could go advance one more. If you could squeeze the sun down to the scale of UCLA's campus, the sun would become a black hole. Okay, so simple, right? Lots of mass inside a small volume, proof of black hole. So hold on to that as we go through this lecture. The next piece is to think about, where do black holes show up? And the story of black holes, I think, is a wonderful demonstration of the 2 common pathways that we engage with science in. So if we think about the stellar mass black holes, and if, Rory, if you could go one more. So this is a picture that shows that from theory, actually we anticipated that the most massive stars in our galaxy would evolve through their life and end their lives as supernova, which is what you're seeing here. So these are stars that explode. They start their life off with roughly 30 times the mass of the sun. At the end, there's an explosion. The outer layers go off. doing all sorts of really important things. So supernovas are really important for all sorts of things, but why, from the point of view of this lecture, what we care about is what's happening on the inside. On the inside, rather than expanding, there's actually a contraction to becoming a stellar, what we call a stellar mass black hole. So black holes were first recognized thinking about theory, anticipating how massive stars would evolve. And then observationally, today we have beautiful demonstration that these stellar mass black holes, and they're roughly on order of 10 times the mass of the sun. And we find them, I love these rugs, because it's a great demonstration, by two of them orbiting, merging, and sending out gravitational waves into the universe that we can now detect, which is another really big and important advancement in our field. So the case for that's the case for the stellar mass black holes. The case that I care about, if you advance one more, are the supermassive black holes. And you might guess by their names, they're really massive. So rather than being 10 times the mass of the sun, these are objects that are 1 million to 1 billion times the mass of the sun. And unlike the stellar mass black holes, these were not objects that were anticipated by theory, but rather there was phenomena that we saw observationally that couldn't be explained and has been associated with the idea of these really big black holes. So where did this observational hint come from? It came from observations of galaxies. So in the last picture, we were looking at a single star. Here we're looking at almost everything in this picture, except the one thing with the crosshairs in the middle, which is a star. Everything else is a galaxy. Each galaxy has roughly 100 billion stars. So we're on a vastly different scale. This is a picture taken with Hubble Space Telescope. It's sensitive to light that is roughly where your eye detects. In the upper left corner, there's a galaxy that's a spiral-like galaxy. That's a galaxy that would look like our own if we could get back and get outside and look back. There is absolutely nothing in this image that suggests the existence of supermassive black holes. And in fact, if we can advance one more, that hint came from observations at a very different wavelength in the radio, which is more or less where your cell phones work. That's a source of noise, all your cell phones. So the astronomers don't like that. Me personally, that's where you have a little internal conflict. But at radio wavelengths, you see really energetic phenomena emerging out of roughly 10% of all galaxies. These show-offs, I like to call them the Primadonnas of the galaxy world. They're called active galactic nuclei, or AGN for short, because their nuclei, or their centers, are very active. So the scale of all the visible light that we were looking at is just a small section around the central dot. Out from that central dot, you see these jets emanating out from the core. And you can measure the energy in these jets. Just measure how fast they're moving, kinematic energy. And from that, you know that there's a very powerful central engine that's driving this unusual phenomena. Similarly, in the central dot doesn't look like starlight at all. So the thinking that went on at this point, which was roughly 50 years ago, is maybe this phenomena is driven by supermassive black holes that are accreting a lot of material just outside the event horizon. In other words, you can think of these black holes or these galaxies as having a huge Thanksgiving feast. Okay, so this is lighting it up. Okay, so that was the origin of the idea that supermassive black holes might exist. But as you can see, this is a pretty indirect argument and really started a journey in our field to prove the existence of these supermassive black holes. So Rory, could you advance one more? Okay, so this is a zoom in to that cutout that we were looking at on the top left that would be very much like our galaxy if we could look back. And in fact, if we made that connection, our sun, our solar system, would be roughly halfway out in one of these spiral arms. Now we're going to look towards the center of the galaxy because that's where we think these supermassive black holes exist. And almost every way you can describe a galaxy becomes more extreme as you go to the center of the galaxy. So often we like to talk about the center of the galaxy as being the urban hub. So think downtown New York. And we live out in the suburbs. Low density, so stellar density, low, not too crowded, things aren't moving too fast, and all sorts of other phenomena that you can describe at more extreme as you go to the center of the galaxy. This is going to become important later because it means that there's a lot of astrophysics that can be studied at the center of the galaxy, in addition to just the question of whether or not a supermassive black hole resides there. Okay. So we are interested in looking at the center of the galaxy. So Rory, could you advance one more? Now we have a really unique vantage point in terms of looking at the center of our own galaxy. So galaxies tend to be flattened disk-like structures. So what we were looking at was something face-on to look at the structure. When we're looking at the center of the galaxy, we're looking at something edge-on. So this is a wonderful photograph that was taken by Brad Lewis on the Big Island, where you can actually see the plane of the Milky Way, and you beautifully see that. All that light, that white pathway, is the plane of the galaxy. You'll also notice not only the light that comes from all the stars in our galaxy, but the dust, the lack of light. And that comes from all the dust that is in the plane of the galaxy. Now, we live in Los Angeles. We have a visceral sense of what dust in the atmosphere does. And it turns out the dust in the galaxy is really similar to the dust that produces smog. It's really good at blocking optical light, the light that your eye detects. So that's what's showing up here. So you can think of dust as being a really good blocker of light that has a wavelength that's roughly the size of your dust particle or smaller. So if you go to longer wavelengths, the light can actually penetrate through the dust, and you can see the center of the galaxy. And back comes the central role of infrared astronomy, because infrared light has a wavelength that's just longer than what your eye detects, and it can penetrate through all that dust in the plane of the galaxy. So you can actually see the center of the galaxy. So that's why infrared technology has been so central to this story. And in fact, there have been many technological advancements that have enabled us to do this work. And one that often is under-recognized is advancements in the infrared detectors. So in fact, when I was a grad student, I had already started to think about this project, but the read noise was too noisy for this project to be possible. So one thing that had just happened in the early to mid 90s was the infrared detector technology was getting really good. So you could be sensitive to those poor photons that have to make it from the center of the galaxy to us. Okay, I'm going to say a little bit more. Actually, I'll say it now because I'm thinking of it. One of the things that I think is really profound about astronomy and astrophysics is to realize that effectively you're getting an amazing history lesson because of the finite speed of light. So it takes light 26,000 years, which on astrophysical terms, that's just yesterday. But we are seeing things that evolve on a human timescale, as you'll see, that really originated 26,000 years ago. And there are a lot of accidents along the way. And I'm going to get to another one in a second. So just keep that in mind. All right, can we go to the next slide? Okay, so in order to prove that there's a supermassive black hole, we want to show that there's a lot of mass inside a small volume. I'm just looking at the timer. And the way we're going to do this is directly by looking at the motions of stars. So stars are going to move under the gravitational influence of whatever is inside their orbits. That's the same reason that planets orbit the sun. It's just gravity. So that each star, if you can measure the whole orbit, tells you how much mass is inside its orbit, and the shape of the orbit tells you the region that you've confined it to. So remember, you want to show a lot of mass inside a small volume. So you want to get to the stars that are as close to the heart of the galaxy as possible. So you're really inward bound in this experiment. You want to see the stars that are at the heart of the galaxy. Could you proceed to the next slide? Okay, so that tells you why I wanted to get access to Keck. Keck is the largest telescope in the world. And there are two campaign promises of big telescopes. One is that, oh, and let me just say that we characterize telescopes by the diameter of the mirror. So you can see the telescope dome, you can see the structure, and at the back, on the left side, you can just barely see the mirror that's collecting the light. So we characterize the telescopes primarily by how big that mirror is, the diameter. This is a 10-meter telescope, and just to give you a sense of scale, that's like a width of a tennis court. So these are enormous. And in fact, one of the innovative things about this facility was that a UC astronomer came up with a new design for building mirrors. So rather than building one single glass mirror, you build 36 hexagonal segments and you put them together, and in a feedback loop, you control them to a fraction of the wavelength you want to observe it at. Okay, so this is a non-trivial problem in itself. So that was very controversial roughly, well, in the 70s and 80s, and people thought UC were nuts for suggesting this, and yet all future telescopes pretty much are designed with this technology. So this is a huge win for the University of California. Okay, so big telescopes are good because you've got a big mirror, you can collect light and see things that are very faint. So that's first campaign promise that most astronomers have been pursuing. It's actually the second campaign promise that I find particularly intriguing, and that's that the larger your telescope, the smaller the angular resolution that you have. In other words, the better your ability to distinguish small details. So the analogy I like to make here is to the art technique of pointillism. So in which people paint by dots. The closer that you stand to the painting, the better your ability to see the individual dots. So having a big telescope, in principle, is like getting closer to the universe. Okay, but of course, this is just your angular resolution, your ability to see the dots. Can you go to the next one? Oh, right. I was going to ask you, but now I've told you the answer, which is, where do you build such a telescope? There's lots of controversy surrounding where you put telescopes in the world, and there are a lot of things you have to think about in terms of where to put them. And it turns out that one of the premier places in the world is in Hawaii. So they're on on Mauna Kea, on the Big Island, and there are a couple of reasons. So I think this is where now you're seeing I can't remember if I stuck this segment in. Can we go one forward? Oh yeah, I did put the segment in. Okay, so there are a couple of reasons. One is that you get above the clouds. All the rain is not good. So you want to be at a very high peak. So that's reason number one. If you could go one more slide. You want the airflow, so you'd like to get above as much air as possible, but you'd also like whatever air is left, because we know there's air at the top of these high peaks, to be a very smooth airflow. And it turns out, this is according to the atmospheric scientists, we've been talking to a lot of people, that airflow is very stable over big bodies of water. So you'll find that many of the largest telescopes in the world are located on mountain or volcanic peaks located next to large bodies of water. The other next thing that we're going to look at, can you go forward next, one more, is that we don't like light. We're trying to see faint light, so city lights are a bad thing. And this is where this is one of the areas in which the desires are in opposition. So you don't want city light. So and this is a wonderful mosaic of the world at night, so you can see where the developed world is. But you want access to high technology. And those two things tend to be in direct opposition. So Hawaii is one of the few places in the world where it's fairly isolated, and there are a lot of city ordinances that keep light pollution at a very low level. Okay, so there's a nice synergy between the local community and the astronomers in terms of light pollution. Okay, can you go forward? Okay, so there are about a dozen facilities up on the top of Mauna Kea from all around the world. So it's not only UC and Caltech that are up there. The Keck telescopes are the two things that look like tennis balls in the relative foreground, but you have telescopes from France, the United Kingdom, China, Japan. It's an incredibly international place up there that just reflects the scientific value of this site. Okay, can you go forward once? Okay, so great place. So what's the problem from a scientific point of view, or the challenge for looking at the center of the galaxy? And the challenge is shown here. This is actually some of the first data we took in 1995 when we finally did get on the telescope. And the problem is the atmosphere. The atmosphere is great for us. It allows us to survive here on this planet, but it is a complete headache for people who want to study the universe. And the problem is, okay, so now think back. Light traveling for 26,000 years, hits the top of the atmosphere, lasts 30 microseconds. It gets completely distorted by the atmosphere. So, my joke is, accidents happen close to home, and that's definitely happening here. So much of my research has been focused on how do you recover the underlying structure or disentangle it from what the atmosphere is doing, and the atmosphere is changing constantly. This is a math problem. Okay, so this is deconvolution. How do you tell what you're trying to look at versus the interfering effects of the atmosphere? Okay, so we've used all sorts of different techniques, and in fact, this is an area where there's been tremendous progress in the last 2 decades. There's all sorts of solutions to this problem. Okay, so if you advance one of the most obvious solutions is you get above it. I mean, that definitely solves the problem, right? You don't have to deal with the atmosphere if you're above it. So that's the solution of Hubble Space Telescope, which has been successful, incredibly successful, but it's a small mirror. The mirror is 2.4 meters in diameter. So remember, our telescope is 10, and the kind of science that I do, the benefit of the resolution goes as the diameter to the 4th power. So it's not just a factor of 4, but a factor of 4 to the 4th power. So you basically have almost a factor of 100. So that's worth working at for. Okay, so, and then the side comment, because many of you will be aware of, James Webb is also being launched. It's supposed to be, if all goes well, December 18th. And that's a 6-meter telescope. So still 10 meters bigger than 6. Of course, we partner very nicely because James Webb gives us the big context, and what we do with Keck gives us what's happening really at the center. Okay, can you go one more? Okay, so my group has been very focused on overcoming these distorting effects of the Earth's atmosphere. We can actually get to the highest resolution afforded by the Keck Telescope. In other words, these technologies effectively enable you to think about, it's like bringing Keck to space, but doing it from the ground. All right, so the 5 brightest stars, the bug spots that we were looking at a moment ago, and these technologies allow you to see what's going on. And what's particularly important is what's going on in the middle of the box. That middle of the box is where we think the black hole is. I haven't told you why, but there were reasons. You can ask me later why we focused on that area in particular. But we're pretty sure that that's what defined the center of the galaxy. So it's the stars in that box that you want to watch move or measure how they move, but you have to measure thousands of stars to do this experiment. Okay, can you advance one? Okay. Oh, right. I love showing this picture only because it's like showing the early instrument. So the other wonderful thing about Keck Observatory is that because it's a university-owned facility, they actually let professors and their groups modify the instruments. This is an incredible privilege. So, when I first got here, we made the small modifications that allowed us to do what I call the simple technique. Well, it's a very simple, inexpensive way of getting to the diffraction limit. So for beating the atmosphere, or you could say taking the twinkle out of stars, all we had to do is change the electronics so you could read out really quickly to keep up with the atmosphere without driving the read noise of these precious infrared detectors high. And you needed to put in some optics that changed the plate scale. This is like, for me, is like a baby picture because now this instrument is now taken out of the telescope. So this was the day we were putting it to rest, so to speak. Okay, so that was a decade ago. What are we doing today? Today we do something much more powerful. So for the first 10 years, we took these short exposures, and it was all about computational methods of doing these deconvolutions. So a lot of coding and deconvolution techniques at that time. But it was always understood that if you do this in hardware, in other words, if you undo the effects of the atmosphere in hardware, you're going to be much better off. Okay, could you go one more further? Okay, so this shows you on, all right, so this shows you on the left, the problem of the atmosphere. On the right, if you advance one more, it's going to show you one image per year. So rather than every 10th of a second in a given year, it's the early technique. So again, like the early home movies, remember, the first proposal was turned down because they didn't think we could see stars. Our technique wouldn't work, we couldn't see stars, and we wouldn't see it move. You don't need a computer to tell you that there's something really interesting going on at the center of the galaxy, because those things are moving really fast. That's 1 year at a time at the distance to the center of the galaxy. You can probably find my favorite star in the entire universe. It's not one of those on the LA star maps, but it's there. Its name is SO2. And it's the one that has the most power to tell us what's going on at the center of the galaxy. And it continues to be the focus of much of our work. So if you could proceed one more. So more recently, we use adaptive optics, which is a way in hardware to undo the distorting effects of the Earth's atmosphere. So one way of thinking about what's going on here is that the atmosphere is like a circus funhouse mirror that makes the object look distorted. And what we're going to try to do here is put a second mirror that's conjugate or has the opposite shape to make things look flat again, so you can actually get those pristine images. This is a wonderful animation, but a couple miracles happen, like the dome goes away. So we can get us insight into how light propagates through the system. So you're going to see two depictions of light going through the system. The first one shows the beam of light. So it's going to bounce off the primary mirror, the one that we are always used to describe how big a telescope is. It's going to bounce off a secondary mirror up at the top and then go through a hole in the middle, which is a very common place, but not the only place that you can put instruments. So now we're going to look at the instrument bay. And the walls of this bay are going to disappear. And we're going to look at the inner workings, or the key elements that are important for how an adaptive optic system works. So an adaptive optic system tries to do this counteracting of the Earth, of the atmosphere. The magic, the real key is in that top right element. That's called a deformable mirror. So you re-image, or you make a copy effectively of your primary mirror, and you want that mirror, which is much smaller and more nimble, to take the opposite shape that the atmosphere puts on it. So in a minute, we're going to look at wave fronts. So this is another depiction of light. If there was no atmospheric problem, they would be flat, but instead they look like Pringles potato chips. And so the goal here is in the feedback loop, where you look at something that tells you what's going on in the atmosphere, you flatten it out, and you've got those flat pancakes, and then you get to the highest resolution possible. So you can see there's some key hardware issues. You have to move a mirror around at 1,000 times a second to make this work. So advances in hardware have been key, and then you need to computationally to do these calculations very quickly. Okay, so those are two arenas that have been very important. The third area that's been really important, Rory, if you could advance one more, has been how do you look at something that's bright enough to tell you what's going on? And what we do today is we shine a laser, this is like Star Wars, up into the atmosphere. And by a complete fluke of nature, there's a very thin layer of sodium atoms that's trapped at 90 kilometers. Those sodium atoms come from meteorites that are burning up as they go through the meteors as they go through the atmosphere. So when you're camping and you see a shooting star, it's not a shooting star. It's this burning up meteorite, which is basically resupplying our sodium layer, which we love. Okay, so it's a very thin layer that you can take a laser that's been tuned to a transition in the sodium atom and stimulate those sodium atoms to shine. Okay, so that's the key. And this is remarkable technology that was primarily developed in the military, because of course the military also cares about looking through the atmosphere, both up and down. And in the early 90s, it was recognized that the astronomers were making enough progress. So why should the federal government fund the astronomers when in fact they've already done this in a completely different field. So there was a really interesting moment in the 90s when this happened, and then it became all about trying to figure out how to apply this technology in an astrophysical setting as opposed to a military setting. There are, your objects are much further away, it turns out. All right. So that's the technology. Let's go one more slide forward. Okay, so now if you recall that tiny little square that I said, those are the stars you care about, this is actually a fourth of the real estate because this animation has gotten so confusing over time. This is now no longer real data. The last one was actual data where you could see how stars were moving. This is a depiction of how we tracked the stars. You can see my favorite star, SO2. It's trailed in a yellow line. And once you see things with an image, it's trailed with a dashed line. And then once the technology is such that you can get the spectrum, I haven't said anything about spectra. It's a way of measuring wavelength changes that come from the motion of objects towards and away from you. Okay, if you don't, that doesn't make any sense, I'll just say it's how you get a speeding ticket. Okay, those radar guns, the wavelength of light is measured as it bounces off your car. Okay, so that's been the next development. And once things are measured spectroscopically, you're trailed by a solid line. Okay, so SO2, why is SO2 so important? It really is the most powerful star in the system. So if we could advance one more. Before we started this experiment, we knew that there was 4 million times the mass of the sun inside this giant circle. And this was work done by Charlie Townsend's group up at Berkeley. And yet there was no mention of black hole in the title, in the abstract. It's buried in the paper, and that's simply because that circle is so big compared to the Schwarzschild radius. So what does this experiment do for you? So if you could advance one more. It demonstrates that inside SO2's orbit, there's still 4 million times the mass of the sun inside SO2's orbit, which effectively confines the volume that mass is confined to by a factor of 10 million. So in other words, this has taken the evidence for the existence of supermassive black hole and advanced it by a factor of 10 million. I mean, that's been a huge, huge step forward and has really actually fundamentally gone in two big giant steps. The first 3 years, which was really our vision, which was just measuring velocities, was the first factor of 1,000. But 3 years into it, we understood how much better all of this was going to work. It was going to work. Well, it was working far better than our wildest imagination could have possibly told us. So in the ensuing years, we've gotten the next factor of 10,000. Okay, so one more slide forward. Now we have the strongest evidence to date for the existence of a supermassive black hole in our galaxy. Sorry, it's a better evidence for our oh my gosh, don't look at time, right? We have the strongest evidence to date for the existence of a supermassive black hole anywhere in our galaxy, and it just happens to be in our own backyard, making the center of our own galaxy a wonderful laboratory moving forward for understanding the physics and astrophysics of black holes. Now I'm going to ask Rory to do either, if he can jump to the 3D animation, if he knows how to do that, or we'll just advance through. Yeah, okay, thanks, that's perfect. Okay, so there's a lot, one of the wonderful things about new technologies is it gives you a vastly different way of seeing the universe. And when you make transformative changes in your technology, you get such new views that not only can you answer the question that you set out to answer, but often you see questions that you didn't think to ask. And so that's why I really wanted to emphasize that the center of the galaxy is a really exciting place. It's really rich in astrophysics. So in fact, almost every prediction that you could make for what you should see at the center of a galaxy around a supermassive black hole has been inconsistent with the observations. Now, there's two ways of thinking about that. One is job security. And believe me, in my early days, that's probably how I thought. Today, I think kid in a candy shop. Like there's so many more interesting problems to do. And just to give you a little taste of what's so fun about this work today, or some of the problems, one of the predictions is that near a black hole has lots of gravity, and in particular, what's known as the tidal forces, which is the difference in the gravity. Like if I was falling in towards the black hole first, the pull of gravity at my feet would be much stronger than my head, and I would be torn apart. It's why in the movie Interstellar there are those giant tidal waves on the planets near the supermassive black hole. So you don't expect young stars because they should be torn apart. They start off as fragile clouds of gas and dust, and so it should inhibit star formation. So prediction 1 is no young stars. Prediction number 2 is old stars have been around for a long time, so they can form far out, and the dynamics, or in other words, the interaction between all the stars and the central black hole is things just want to congregate around the most massive object in the system. So there should be an entourage of things, old things, near the black hole. So lots of old stars. So let me decode this animation for you. The greenish things are young. Okay, remember there shouldn't be any. So I like to call that the paradox of youth. There are young stars where there should be none. Okay, so how did these young stars get formed? And as this animation pulls back, you'll see that there's a hint in the structure of the orbits. And in fact, it looks like a scaled up solar system. So we're actually learning a lot from looking at how planets are formed in solar systems in terms of what might be happening here. In fact, the idea is quite similar, that you have a very massive disk that forms these young stars, and then the disk dissipates. So that's one of a myriad of ideas that have been put forward. The orange things are the old stars. Remember, there should be lots. There are very few. So again, what's going on? And then the third is color coding that I haven't mentioned because there were no predictions for are the pink stars. The pink objects are objects where you actually see them come close to the black hole, and as they come in, they lose. You can see this in real time, like human timescales. These things lose their outer envelopes. They come by the black hole, and then they become more compact again. To get that to happen, these objects have to be 100 times larger than anything we made predictions for. So my favorite, this was a perfect gift. My favorite mechanism is most stars are formed as binaries. Black holes and binaries have a 3-body interaction. And the evolution of that can be that it forces the binary star to merge. When stars merge, they become bloated for about 100 million, 10 to the 5th years, so 100,000 years. That's short on stellar lifetimes, but can produce these pink objects. And we think that's got some interesting connections to gravitational waves that I can talk about if people are interested in later. Okay, so lots of mysteries. And I think what I want to do, Rory, if you would take me to just the end of the presentation. Yeah, that would be great. Okay, lots of tests, lots of new technology, but the technology I really would be remiss if I did not mention is the 30-meter telescope. So the 30-meter telescope, is the picture of the telescope the one before? Yeah, thanks. And hopefully this will play. It might not. Okay, so this is the 30-meter telescope. It's the next big thing for the University of California. So the Keck Telescope is UC and Caltech. This is UC plus Caltech plus Canada, Japan, China, and India. It is a really exciting, ambitious project. To give you a sense of 30 meters, remember we said 10 meters like the width of a tennis court, now we're talking about the inside of a baseball diamond. And rather than 36 hexagonal segments, we're actually going smaller to 492 little segments that have to be coordinated. So lots of interesting engineering problems, both on a hardware, mechanical, and software perspective. Today, at the center of the galaxy, we only see the tip of the iceberg. So if we could go to the next one. With this facility, so this is, on the left is where we are today. We're advancing adaptive optics, which will both increase the scientific reach of Keck and mitigate technical risk for the 30-meter telescope. So the thing that's useful to understand about the center of the galaxy and where we are today is we can only see the brightest stars. The faint stars, which are more common, get lost in a sea of the background. So one of the things that I often think of it when we see these things that we don't understand with these observations that just show us the brightest observations is that you can be at risk for only seeing part of the story. And the analogy here would be trying to understand the economy by only studying the biggest transactions, which are large but infrequent. Like stars, the bulk, lots of important information comes from those smaller but much more frequent interactions. So today we can't see stars like our sun at the center of the galaxy. So lots more to come. So I think we've got the last one at the end here. Yeah. Okay. So if you want to learn more, check out the UCLA Galactic Center Group website. And if nothing else, I hope I've convinced you that we have a supermassive black hole at the center of our galaxy, and we've ended up with more questions than answers and a wonderful laboratory for understanding both the physics and astrophysics of black holes. Thank you for your attention.